We'll get started today. So as you'll recall, today is all review now. So I'm assuming all of you have taken the third exam, which is why you're here now, not taking the exam, which is still going on for some people. And if we want to keep in mind in where we are, so today we're going to start the final exam review. We have part 2 on Friday. And I realize it's not ideal to divide the final exam into 3 parts, but it was really unavoidable because on April 29th, which is the last day of class, that's going to be our final exam review part 3, as well as course evaluations. We have to cut short a little bit on that day to make sure we can do the evaluations. So those are the remaining things after today. So we're sprinting to the finish line or stumbling to the finish line, however you want to think about it. But we are getting close one way or the other. All right, so that's going to be sort of what's coming up left, just all review. So what we're going to start with today, the title is Hodgepodge, which is basically just a collection of topics that, having now, this being my, I think, 5th time teaching this course or so, these are the topics that when the final exam comes back around, students seem to have particular trouble with for various reasons, either because we didn't cover it very well earlier, or just because it's a topic that we've forgotten about. So I'm going to try to pick a few that I think are difficult, and also some that I think will play into a whole lot of, several different questions on the final. So they're going to be sort of key concepts that you're going to want to know for a lot of things that we do. All right, so let's get into it then. The first thing that often gives a little bit of trouble is trends for ionization energy and electron affinity. So this is where we can use the periodic table to figure out, at least in a relative sense, what the electron affinity or ionization energy is for a certain element. Now, the general trend for both of them is that they increase left to right. So they both have the same general trend of increasing left to right, as well as increasing bottom to top on the periodic table. So as we go across a row of the periodic table, in general, they both increase. And as we go up a column from lower to higher on the periodic table, they're going to also increase. So that's the general trend for these. So this is all for, again, periodic trends. We're talking about the periodic table here. But what we have to keep in mind is that there are going to be some exceptions to this trend. And the reason that these exceptions exist is that there are certain electron configurations that are particularly stable. So we have to recall the definition of ionization energy and electron affinity. Ionization energy is losing an electron, the amount of energy it takes to remove an electron from an atom. And electron affinity is the enthalpy change when an electron is added to an atom, so when an atom gains 1 electron. And so if you have a particularly stable electron configuration, the element is not going to want to gain or lose electrons. It's going to want to stay where it is, relatively speaking. All right, so stable configurations that exist, and we don't have to worry about precisely why these are stable, but we should remember them, is that, so NS2, which is a filled S subshell, so that would be the group 2 elements, starting with beryllium, magnesium, and on down. So those elements are going to have relatively stable configurations. If you go to the half-filled P subshells, that would be the group 5 elements, starting with nitrogen, phosphorus, arsenic, and so on. So those elements have relatively stable half-filled P shells. And then the most stable configuration for the main group elements is going to be the noble gas configuration, NP6. So when you have one of these as your valence configuration, they don't want to lose or gain electrons. All right, so they want to stay at those configurations and not add or subtract electrons to go to something different. All right, so what that means then is that since ionization energy is the amount of energy required to lose an electron, those ionization energies are going to be exceptionally high when the atom has these configurations. So ionization energies are exceptionally high for those configurations. And the group numbers that those correspond to are going to be 2A, which is the NS2 configuration, 5A, which is the NP3 configuration, and the noble gases 8A. This is how they're labeled on your periodic table with Roman numerals. All right, so those are the group numbers that have exceptionally high ionization energies. And then electron affinity, those same groups is where the exceptions occur, but it's going to be exceptionally low in those cases because electron affinity is basically how badly does that element or that atom want another electron. So if it's at a stable configuration, it doesn't want another electron, which means it has a low electron affinity, relatively speaking. So electron affinity is going to be exceptionally low for those same groups. The reality also is that for group 8A, which is a noble gas column on the far right, we don't even have well-defined electron affinities. It's basically impossible to even add an electron to those and measure that affinity, so we don't even really consider that as part of the trend, but it is exceptionally low if we were ever wanted to think about it. So then what we can do is we can put these trends onto a little bit of a plot as a function of a group number. So as we go across the groups of the periodic table, so remember we're talking about the main groups here, so let me point that out where that is on the periodic table. So we're talking about the A groups, which are the main group elements, so 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Those groups on the periodic table as we go across, how does the electron affinity and ionization energy change? As we said, the general increase is left to right, but we have these exceptions. So in blue, I'm going to show ionization energy. So ionization energy in blue. So it starts out relatively low for group 1A, and as we said, it's going to generally increase as we go across. There's a large increase from 1A to 2A, and this one is going to be exceptionally high, higher than you expect it to be for ionization energy. So when we go to 3A, it actually goes back down. All right. So again, this group 2A here is one of our exceptions where it's even higher than we would expect it to be following the trend. If we go from 3A to 4A, it's again an increase, but a pretty steady increase. And then group 5A is another one where the increase is larger than we expect, and it goes even higher than that, and it comes back down for group 6A. 6A to 7A has, again, a steady increase, but not a huge increase. And then 8A is basically off the charts, so I'll just put it somewhere up there. All right, so the general trend, if we were to draw a trend line through this, is that it does increase left to right, but we see that at these two positions, those are even higher than we expect, and when we go left to right from those groups, it actually goes back down a little bit, okay? So those are the two places we have to remember where we have exceptionally high ionization energies, and as we go across the groups here, we have these slight blips in the trend. And then similarly for electron affinity, again, just drawing this on an arbitrary scale, we would have, let's say we'll start about here should work. So group 1A, we have a relatively low electron affinity. Electron affinities are typically exothermic, but when we say it has a high electron affinity, that means it's more exothermic, more negative, okay? And so electron affinity for group 1A is relatively low, and then as we go to group 2A, we have an exceptionally low electron affinity, so it's going to be, again, below the trend line. 1A to 3A, we have a pretty steady increase. 3A to 4A, an increase. And then we said 5A is the other place where we have sort of this exceptionally low electron affinity, which lies way below the trend, I should say. So this one's, these are typically positive numbers. So I'll put it again down there. These are arbitrary scales. And then 5A to 6A, we have sort of another increase, and then 7A, another increase. All right, so again, a pretty steady increase for most groups, but with 2A and 5A for ionization energy, which I'm going to have in red in case that wasn't obvious, electron affinity in red, those are going to lie below the trend. Okay? So for electron affinity, we have the same spots where the trend breaks, but this time we have a decrease in electron affinity at those positions, a lower electron affinity than we expect. All right, so in general, you can use the trend of going left to right, where both of these increase left to right, but you have to remember that there's places where there's discontinuities, and those occur at group 2As and group 5A. Group 8A, as I said, we don't even have a well-defined electron affinity, but it is very low also. All right, any questions on this topic? Yeah. we're not going to worry about, so if you're talking about electron affinity or ionization energy, we don't really worry about those for transition metals. I think they generally have the increase left to right, but it's not, again, there's a lot of, differences between group numbers that are not predictable. So we're only going to worry about these trends for the main group elements, the group A, the ones that are labeled with A on the periodic table. So that'd be the S block and the P block. So any of the transition metals, it's not as easily predictable. All right, other questions? Yep. Well, so for second ionization energy, you have to think about also the electron configuration as well. So typically for second ionization, if we're asking you to compare that, you want to look at whether or not it's still removing a valence electron or a core electron. So for second ionization energy, if you're in group 1, you have to remove a core electron, so that's going to be really, really high, and higher than any of the ones that come after it probably. So for anything beyond the first ionization energy, this trend does not exactly work. You have to think about first whether or not it's involving valence or core electrons, and then try to rate them in that regard. All right, anything else? All right, so the next major topic I want to make sure we're clear on is the various ways that we have for determining moles. So we introduced this, back in chapter 5, about halfway through the course, and we've been using it nonstop ever since then. And we now have, basically, as I'm showing here, 4 different ways of determining moles. And those are going to come into play on their own in some problems. They're going to come into play in a lot of the stoichiometry problems we do, and even some of the stuff we saw from chapter 7 and 8, which wasn't stoichiometry, but involved, gas laws and, thermochemistry and things like that. We still had to do a lot of mole calculations. So let's make sure we know how to do this. So moles of substance is sort of the key quantity in chemistry that we use. And we now have a lot of different ways of relating that. So the definition of a mole, as we first introduced, is that it's Avogadro's number of entities or particles, however you want to think about that. So if we want to think about the number of entities in one mole, which would be, again, atoms or molecules, we use Avogadro's number. So if you want to go from number of moles to number of entities, you multiply by Avogadro's number. And if you want to go in the other direction, if you have the number of atoms or molecules of your substance and you want to figure out how many moles that corresponds to, you divide by Avogadro's number. All right, so that's the one definition of a mole. And remember, mole is a counting number, so it means we have 6.022 times 10 to the 23rd of anything in one mole. And we think about it as sort of the fundamental building block of that substance. So if it's an element, we would have 6.022 times 10 to the 23rd atoms per mole, because elements are made up of atoms. If it's a molecular compound like water, we would have 6.022 times 10 to the 23rd molecules in 1 mole of water. So it's whatever that smallest building block is for that particular substance, we're going to have Avogadro's number of those units in 1 mole. So that's one definition. The one that we probably used most commonly was the relationship between moles and mass, and this one I think most of us are comfortable with, given how many times we've encountered it. And that's going to be using molar masses. So again, we can go in either direction depending on what the problem is requiring us to do. If we want to go from moles to molar mass, we multiply by the molar mass. From moles to mass, we multiply by molar mass. If we want to go from mass to moles, we divide by the molar mass. So again, it works in both ways, and we can use this molar mass as a conversion factor that relates mass and moles. And then the ones that we learned more recently in Chapter 6, we had a lot of details about aqueous solutions, where we have volume and molarity. So if we know the volume of an aqueous solution, or really any solution that has a defined molarity, if we have that volume specifically in liters, we can use the molarity to convert between moles and volume of solution. All right, so if we want to go from volume to moles, we would multiply by the molarity. And if we want to go from moles to liters of solution, we would divide by molarity. All right, so all these conversion factors work in both directions, whether we use them as in the numerator or denominator of our conversion. So that's what we learned in Chapter 6, which we also use a lot for titration problems and solution stoichiometry in more general terms. And then finally, what we learned most recently in terms of moles is the ideal gas equation, which relates pressure, volume, and temperature of a gas. Should include temperature as well. So if we have all three of those, we can use PV equals nRT to solve for moles and vice versa. All right, so that one is another relationship involving moles. And very often for, again, gas stoichiometry, this was one that came into play, or in other cases, collecting gas over water, we had to find this relationship as being helpful. So don't forget about that. Anytime you're dealing with gases, we can use the ideal gas equation as another relationship involving moles to help us out. So a lot of these tools that I have summarized here, there's not necessarily going to be a problem that just involves this on its own, but these are, key concepts that we have to use for a lot of different types of problems. And so always keeping in mind what types of relationships we have involving moles and being able to use those when you need to is going to be an important thing to be able to do, as you've already seen from the last two exams, and it's going to continue on the final exam as well. All right, so any questions on these concepts before we give just maybe one or two examples of this? All right, so the one type of problem that I want to go over quickly is one that people make a small mistake on all the time. So let's say we have 0.1 moles of ethane, C2H6, and we want to know how many atoms are in there. So what most people do in this is they say, okay, number of atoms is just 0.1 moles, and most of you, or many of you, I shouldn't say most, many of you still don't write your units, so this is where often the mistakes are made, and regrets are had and all that stuff. So we have 0.1 moles of C2H6, and what most of you would do is just multiply by Avogadro's number and say, all right, there we go, that's the number of atoms. But remember, when we use Avogadro's number, that's going to tell us the number of building blocks of that particular substance. Ethane is a covalent molecular compound, so when we multiply by Avogadro's number, that's going to give us the number of molecules of ethane that we have, not the total number of atoms. So if we do this step, that's going to tell us how many molecules we have, but we can't stop there because we're looking for how many atoms. And to figure out the next relationship, we just look at the chemical formula. So C2H6 means we have a total of 8 atoms in one molecule, 2 carbons, 6 hydrogens. All right. So this isn't something we do a lot, I should say. We don't usually need to calculate the number of atoms in a substance, but this is a type of problem that is probably one of the ones that people miss the most, and so I'm going to make sure I cover it really quickly. So the number that comes out is 4.82 times 10 to the 23rd atoms, and again, if we had just done this first step, that would give us the number of molecules, and many of us would then forget to do this last step here as being an important one. All right, so we always have to think about when we use Avogadro's number, what exactly is that referring to? Is it referring to atoms directly or molecules? It is in this case. Always think about what type of substance it is. That's going to tell you then what Avogadro's number is actually referring to in that substance. All right, any questions? Okay. And then using mole conversions was often involved in doing stoichiometry problems. And one type of stoichiometry problem that seems to give a lot of people trouble is ones that involve percent yield. Now, it seems like most people are comfortable calculating the percent yield. So if we say, we did this reaction, we obtained this much product, what is the percent yield? And most of you know that if we want to calculate percent yield, we just need the actual yield, which is typically, in most problems given to us, the theoretical yield, and then we multiply by 100 to get percent. So most of us know how to do this, but for whatever reason, when we have to work backwards, as we do here, it often throws people off. So I want to make sure we're clear on how to approach this. So in this problem, we're producing aluminum oxide by reacting aluminum with oxygen gas. So we write a balanced equation, aluminum plus oxygen gas, remember, is O2, going to Al2O3, which is aluminum oxide. So remember that, again, name to formula is going to be important here as well. Aluminum is here on the periodic table, not the most obvious of choices, but it loses 3 valence electrons to make a +3 cation. Oxygen makes a -2 anion, so the formula for aluminum oxide is Al2O3 to balance the charges. All right, so that, again, make sure we can go name to formula as well, because that comes up in a lot of these also. And then what we had was, to balance this, we just need a 4 there, a 3 there, and a 2 there if we want to use full numbers. Okay? So this is the balanced equation that we're going to use. And as I said, if we wanted to calculate percent yield, this is how we would do it, and most of us seem to be comfortable with this. But now what we're going to do is we want to know if we react 3 grams of aluminum with oxygen gas in excess, how many grams can be made if the expected yield is 50%. So here what we did is we gave you the expected percent yield, and we have to calculate what the actual yield is. So this is actually what we're looking for in this problem. All right. So we're going to solve for actual yield at the end, but first we have to calculate the theoretical yield first. So whenever we do stoichiometry, whenever we do mole conversions and mole ratios, as we're going to do here in a second, that gives us what the theoretical yield of the reaction is. And then if we have the percent yield, we can relate that to the actual yield as we're going to do here. So if we want to calculate the amount of Al2O3 that forms, this is going to be our theoretical yield first that we calculate from stoichiometry. So we're going to start with 3 grams of aluminum. And the first step in any stoichiometry problem is to convert to moles. And as we know by now, if we go from mass to moles, as we just reviewed, you use molar mass. The molar mass of an element is just its atomic mass from the periodic table. So that's going to be 26.98 for aluminum. All right, so 26.98 for aluminum. So we're going to use that as the molar mass. And then once we have moles of one substance, we can relate it to moles of another substance. So we're trying to find the theoretical yield of Al2O3. So we're going to use mole ratios here to go from, we want moles of aluminum to cancel out, moles of Al2O3 to be calculated. So we look at the coefficients. 2 moles of Al2O3, coefficient of 2, per every 4 moles of aluminum. And then the last step is going to be using the molar mass of Al2O3 to figure out what mass of that forms. So now that we have the moles of this substance, we can use its molar mass, which I'll not calculate, but it's going to be 101.96. 101.96 grams per mole of Al2O3 gives us a theoretical yield of 5.67 grams. So many people, when they do this problem, they're just either not knowing what to do with this 50%, or they're just in a hurry and they're giddy that they finally got a number, and they go here and they circle choice B. But remember that choice B here, 5.67, is the theoretical yield. We're trying to find out how much aluminum oxide can actually be formed using a 50% yield. So if we want to find the actual yield, then we rearrange this equation and solve for that, and it's going to be the percent yield of 50% divided by 100 multiplied by the theoretical yield of 5.67. So if our theoretical yield is 5.67 grams, but we actually only get a 50% observed yield, then the amount of product we expect to get is 2.83 grams, exactly half of that. So that would be choice A here. Okay? Any questions on this? So just make sure that when you do a lot of these problems, stoichiometry problems like this with percent yield, or some of the calorimetry problems that we saw most recently on this previous exam, that you can work forwards and backwards, because a lot of times we'll ask you to go in 2 directions. And the more standard way to do this, the more typical way is to actually calculate the percent yield, but in this case we're working backwards using that as our starting point. So make sure we're able to do that and use those concepts in both directions. All right, any questions on this? All right, I think the last thing that I want to go over in this part of the review before getting into the practice problems for the final exam is bond polarity and also molecular polarity. So we talked about a few different properties of bonds, bond length, bond strength, and then the last one that we covered was bond polarity. And this one seems to be one that just, for whatever reason, it is a tough one to grasp. I'll certainly admit that, but we want to make sure that we're clear on what it means for a bond to be polar and also how we rank bonds relative to each other. So what bond polarity refers to is anytime we have 2 different atoms bonded to each other, so anytime 2 different atoms are bonded, rigorously speaking, the bond will be polar. So we're talking about, again, 2 different atoms from 2 different elements. All right, if it's 2 of the same atom, that's going to be a nonpolar bond, as we'll get into later. But anytime it's 2 different atoms, they will be polar. Now, some elements on the periodic table, they have coincidentally the same electronegativity. So there are some heteroatomic bonds, like for example, carbon and iodine are very close to each other in electronegativity, where it's basically nonpolar, but the electronegativity scale is not very precise. So it would still be considered a polar bond. Really, the only truly non-polar bonds are ones where it's 2 of the same atoms. And when you have this, and particularly when you have unequal electronegativity values, you get an unequal distribution of electron density. Because in the limit of a perfectly covalent bond, the electrons are shared perfectly equally between the two atoms. But in a polar covalent bond, they're going to be hogged a little bit by the one that's more electronegative. They're going to have more electron density closer to the electronegative atom, less electron density closer to the less electronegative atom. And so that's what we mean by bond polarity. Now, often what you have to do on the test is you have to rank polar bonds relative to each other, which bond is more or less polar. And that comes in from the difference in electronegativity, or delta En as we abbreviate it. So it doesn't matter what the individual electronegativities are of the two atoms. It matters what the difference between them is. How different are they from each other? All right, so it's difference in electronegativity. And so the larger that this difference is between the two atoms, that correlates with a more polar bond. If you have no difference, if the two electronegativities are the same, which can sometimes happen coincidentally, but always happens if it's two of the same element bonded to itself, in that case you would classify it as a nonpolar bond. All right, so you have sort of two extremes here. No difference in electronegativity means the bond is nonpolar and the electrons are shared equally, or if you have a very large difference in electronegativity, you get to the limit of an ionic bond where the electrons are completely removed from one atom and you have actual positive and negative ions attached to each other. All right, so those are sort of the two limits, and those limits are defined by how big the difference in electronegativity is. And as I said, it's not a function of what the individual values are, it's a function of how different they are from each other for the two atoms. So if we do a quick example problem on this, we have we want to order the following in terms of increasing polarity. So least polar first to most polar. So when we're doing a problem like this that requires us to characterize or rank bonds in terms of their polarity, I think the first thing you should always do is look for a bond that involves two of the same atom bonded to itself, because that's going to be nonpolar, and that by definition is then going to be the least polar of all of your choices. So if we look at these answer choices, we have SCl, SiCl, PCl, SiSi. This one here is two of the same, so that's going to be a nonpolar bond. That has to be our least polar bond of these choices. Okay. So this is our least polar first, so the only answer choice that could even work now is one that has this as the first or least polar bond listed. So we can cross out A, B, and C because none of those have choice D listed first. Okay? None of those have the SI-SI bond as the least polar. So sometimes a little bit of, I guess you'd call it game theory, can be helpful on exams where just look at something obvious about the answer choices and eliminate a bunch right off the bat. So we know that this has to be the least polar bond. Anytime you're ranking bond polarities, the ones that are nonpolar are the least polar, and that gets rid of three of the answer choices already. So now you're already at a 50% chance of answering this right, even if you just close your eyes and let someone else take the wheel and answer the question for you. You'd still have a 50% chance of getting it right. All right, so but let's actually go through the rest of these now. So we have SCl, SiCl, PCl. They all involve chlorine, so that's going to be helpful for us. So we're going to look for which of these has the biggest difference in electronegativity between the first atom and chlorine. So if we go to the periodic table, electronegativity is yet another of the periodic trends that generally increases left to right. And the remaining answer choices here are actually all fairly simple because they're all in the same row of the periodic table. So we have sulfur chlorine, silicon chlorine, and phosphorus chlorine as our three answer choices. And if you're looking for the biggest difference in electronegativity, if the atoms are in the same row, you want them to be the furthest apart left to right. Because the ones on the left have the lowest electronegativity, chlorine, which is all the way on the right, is the highest, and the ones that are farthest apart left to right are going to have the biggest difference between the two electronegativity values. So between these, sulfur and chlorine is going to be the most similar. It'll still be polar, but those are close together. So that's going to be the least polar of the polar bonds. Phosphorus and chlorine then next, and then silicon and chlorine is the farthest apart. That's going to be our most polar bond. So going back to the answer choices, what we want then is, as we said, sulfur and chlorine are right next to each other. So of A, B, and C, this is going to be the least polar, followed by phosphorus, chlorine, which are two atoms apart. So that's going to be next in the middle, and then the two that were furthest apart left to right were SiCl. All right. So choice D is of course still our lowest, but between the remaining three choices, this is the order that we would want, because we want them to be furthest. So the one that's going to be more polar is going to be further apart left to right on the periodic table. And we could have used the same analysis for the SI-SI bond because it's right on top of itself. So of course it has, it's the closest together also from a left to right standpoint. So the answer choice that then works is we want sulfur chlorine next. We want D, then A, then C, then B. So it's going to be choice E here. Okay? All right, any questions on bond polarity? Now the next topic that is somewhat related is molecular polarity. So now we're not talking about unequal distributions of electrons over an individual bond. So bond polarity deals with just two atoms bonded to each other, and again, it's all determined by difference in electronegativity. For molecular polarity, we're trying to consider whether or not there's unequal distribution of charge over an entire molecule. So it's typically going to have more than two bonds, although diatomic molecules we would still be able to classify as polar or nonpolar also. So two things that must be true for you to have molecular polarity is one, that you must have polar bonds. So generally, elemental molecules, things like the diatomic ones, H2, N2, O2, F2, all those are going to be nonpolar because, again, it's just two of the same element. Alternatively, if we had higher order ones like P4 and S8, those are also nonpolar because it's only one type of atom in the molecule, so there's no bond polarity, so you can't have molecular polarity. But that's the first category, but that is a necessary but not sufficient criterion to have molecular polarity. So if you want to use the legal definition, it's necessary but not sufficient. The other thing that you have to keep in mind is the geometry of the molecule. All right, because we have these individual bond dipoles, and in some cases they completely cancel out and leave the molecule nonpolar. In other cases they don't cancel out and the molecule would be polar. All right, so the individual bond polarities must not cancel out. So if you want it to be polar, you can't have them all cancel out. All right. So the individual bond polarities must not cancel out in order to have a net dipole. I encourage you to review, I'm not going to remember the exact date, but if you go back to the notes from molecular polarity from a couple months ago now, I gave you a table that sort of, most of the things we're going to talk about are these AXE structures from VSEPR, and there's a table in there that sort of summarizes which ones are and are not polar, supposing that all of the outer elements X are the same. And most of the ones that we ask you to analyze in terms of polarity are going to be of that format. And so some common ones to remember are that if it has no lone pairs in the central atom, it will be nonpolar. If it has one lone pair, it will be polar. And then there's a few others that are some of each, so you have to make sure you keep those straight as well. So I won't go through all the possibilities today, but you do have to think about the geometry as well when deciding if a molecule is or is not polar. All right. So a typical type of problem we would give you in an exam then is to say which molecule is polar, and in some cases we would also be cruel and say, two of these, three of these, and stuff like that. So this one's a more straightforward one where you just have to pick the polar one. So if we go through the answer choices, the first one is COF2. So if we draw the Lewis structure of this, we start with single bonds to every so that is all the electrons that we have. To complete the octet and carbon, we put a double bond there. So I'm not going to go through the full details, nor do you need to necessarily do that for this, but what we should recognize is that this is a trigonoplanar structure. So this is technically AX3, but it's probably better described as AX2X primes. It has two different outer atoms. It's not the same. So in this case, you would have large bond dipoles from carbon to fluorine, because those are a big difference in electronegativity. Still a relatively polar carbon-oxygen bond, but not as polar as carbon-fluorine. So on the periodic table, remember that you have carbon-oxygen, carbon-fluorine. Carbon-fluorine is farthest apart here, so you're going to have the carbon-fluorine bonds are more polar than carbon-oxygen bonds. So because the three bonds are not equal polarity, you don't have them all canceling out with each other. So in order for them to cancel out, they'd have to all be the same. In this case, you have two bonds that are really polar, one bond that is not as polar, and so you have a net dipole pointing in this direction. So this molecule would be polar, even though it could be classified as AX3. So remember that this shortcut of AXE with no lone pairs, you think, oh, it must be nonpolar. That only works if all the X's are the same. In this case, they're not. So if you have two different outer atoms, typically they would be polar. Okay? So this one's going to be our polar one. We can verify the rest that are nonpolar, so I'm not going to go through all the details. But if we have SiH4, if you do the AXE notation, it comes out AX4. Again, no lone pairs, only one outer atom, so that would be nonpolar. C2H4, the geometry is not as straightforward. There's two carbon atoms, so it's not a very difficult one to draw. But an important shortcut that we've introduced, especially recently in the context of intermolecular forces, that any hydrocarbon, anything that only has carbon and hydrogen in it, will be nonpolar. So for these hydrocarbon molecules, you don't even have to necessarily draw them out. They're all going to be nonpolar. The reason for that is because in a hydrocarbon structure, carbon never has lone pairs, so it's always going to be one of those AX whatever structures, and all the bond polarities, which are pretty small anyway to begin with for carbon and hydrogen, all those are going to cancel out. And then finally we have SF6 and BeCl2. SF6 comes out to AX6. This one is actually, again, looking for ways to help yourself on the exam without, to save some time, especially if you have SF6, remember that the highest number of electron groups you can possibly have in our system is 6, so it can't have a lone pair. It's going to be AX6 and that's it. You can't have AX6E or AX6E2, so for this one you don't even need to really go through all the steps of drawing it. You can know that it's going to be AX6 because that has to be with 6 electron groups. That's the only possibility we have if there's 6 atoms as the electron group specifically. And then BeCl2, we get AX2, which is a linear molecule. Any linear molecule with the same outer atoms, again, will be nonpolar. So all the rest of these primarily fall into that shortcut. If anything with no lone pairs in the central atom will be nonpolar. So A is the only one that would be polar in this set of molecules. All right, any questions on bond polarity or those topics before I jump into the actual review problems? Okay, so we will stop there. I'm going to actually do 2 videos today so that people that are most interested in the final exam review questions can find them easier. So I'm going to stop this so you guys get like maybe